Hello, so we're back on the asteroids and we're going to have a quick look at some timing. But first, a bit of a history lesson. So I'm sure you're all aware of the game Space Invaders, where you've got your ship at the bottom and then you got aliens coming along the top and you're shooting the aliens, and you can move right and you can move left, and you got all these aliens slowly coming down, and then they eat you. Okay, so let's think about what the computer is actually doing. If we built this game in Pygame, we'd probably have this as a sprite, and in the update loop we change the position of the sprite a few pixels to the side, and then the next update we change it a few pixels, and so on until we get to the end, and then we move it a few pixels down, and then we start moving it to the left. Okay, so every update loop is going to go to the alien, move it a few pixels. It's all good and well if there's just one. Now think about if we have more. Instead of just the one alien, we have 4 aliens. So now on the game loop we need to move that one, and then we move that one, then we move that one, then we move that one, and we render it. Then we move that one, then we move that one, then we move that one, then we move that one. So that's a bit more work than it was with just one alien. Now imagine you got a whole screen of them. That starts to take a lot longer than just doing it with one alien. In the original Space Invaders, you may know the game, and as you get less and less aliens, they get faster and faster. You should be picking up on why that is the case now. Yes, it was due to the limitation of the hardware. It was pretty much a glitch that the aliens got faster and faster. It wasn't initial design. It was just because when there was a screen full of aliens, it would struggle. It was going as fast as the computer could manage. So that was quite lucky in that that was one of the first difficulty curves in a game, and that was fairly accidental. But we don't want that to happen in our game. We want control over the difficulty curve and how things were manifested and all the rest. Asteroids, I believe it was on specific devices, so it would always play the same because it was always on the same device. You don't particularly want somebody on one sort of computer having a huge advantage over someone on a faster or slower computer. Imagine if you had a lot slower computer playing this game, the aliens would move so slowly that it's quite easy to win. So we need to do something in our game to make sure that it just doesn't race through, and in a fraction of a second all of the aliens go all the way to the bottom and kill the user just because they're on a fast computer. Okay, let's have a look at the code again. So we've got the game and we've got the setup for the game. What we have been doing is getting the start time and doing things with the system clock, but we can start doing things a bit better and have a clock in the game. And Pygame has a clock, and we're just going to store it as self.clock, and it is pygame.time.clock. And this allows us to measure the time between frames and do a few things like that. Now, when we're playing, we can quite simply say self.clock.tick, and then we put how many frames we want, frames per second. 60 is probably a reasonable frame per second to aim for. Now, this means that when the code goes all the way through the loop and comes back to here, if it hasn't been long enough for there to be 60 frames in a second, then it will wait. So this will slow your game down, so that's the fastest frame per second is going to be 60. We could make it more, we could make it less. So let's have a quick look at how this game now plays, that we've put this frame rate limiter on it. So you can see this is suddenly a lot slower. Okay. Now let's change the frame rate to be a maximum of 120. So that's going a bit faster. What can we actually max it out at? Okay, so we're still getting a little bit faster. Now that's all good and well, but what happens if your computer is slower rather than faster? Or we increase the game so it's doing a lot more work, so it takes longer. Firstly, however, let's have a quick look at the maths, where we've got a frame rate of 240. In every 1 second, it's got to make sure that it can do 240 frames maximum. So if it's waited for this many, if it's been this many milliseconds or less, it will wait until it is this many milliseconds. So it's making sure that there's a gap, so it's not going to do too many. If we have 60 frames a second, if it takes less than 0.01 seconds, so 16 milliseconds, then it's going to wait and just freeze until that amount of time has passed. It's not going to be a noticeable freeze because you're still getting 60 loops in a second, which is a decent speed. Let's have a quick look at the code, because what we can do is we can just sort of hack in the frame rate and see how long it's waiting each time. So let's just do the count first, and if we just keep count of it, because I don't want to be printing this every single frame, because otherwise the print statements would just be ridiculous. So this is just saying every 100 frames print out, and what I can print out is the amount of time between each of the times tick is called. So it runs this code, it will go around again, and then it's going to call it again, and that time difference is going to be time. So with 60 as the limiter, let's have a look, see what actually happens. No, time is a variable which I'm using elsewhere. Let's try that. There we go. So you can see that it's taking 16 milliseconds every time it's going round. We're forcing that because of this 60. If we change it so the frame rate is double, you can see it's 8. So if we had 1 divided by 120, it's 8. We'd expect it to be 4 with 240. There we go. So we can see that there's 4 milliseconds in that sequence. Okay, so this is all good and well, providing your computer is fast enough to keep up with this frame rate, or better it. And we need to make sure that we can adapt so we're going at the right speed regardless if it's a faster or slower computer. And in order to do that, what we use is something called a delta. Now the delta is going to be not the amount of milliseconds, and let's just change that to 60. Not the amount of milliseconds, but the amount of seconds. So in order to get the amount of seconds, we're just dividing that by 1,000. And we can actually see that I haven't updated that. So now you can see that it's 0.016 seconds between the frames. Okay, with that, we've now got some information which we can use for calculating how far the asteroid should be travelling, or how far the bullet should be travelling. So we need to pass this into the update function. Where we've got update here, we can put in delta. Now we're passing delta to all of the sprites updates. Now which sprites are we updating? Well, the bullets, the asteroids, and the ship. So in the updates, that's the main menu. Here's the button, we don't want that. Bullet. So in the bullet, in the update, we want to put in a delta. And I'm just calling it DT just for a shortened form, make it a bit easier. This is the ship, I believe. And this is the asteroid. So I'm taking the argument DT for all of them. Okay, let's start at the bullet. Now what we've got at the moment is the thrust is 10. And in the update, where we've got DT, this is where we're saying, okay, thrust times by how much in whichever direction. What we're doing now is we're going to multiply it by the delta, so multiplying it by this number. So then in effect, the thrust is going to be how many pixels do we want it to move in a second. If we assume at the moment that it's all just on the x-coordinate, so the y-coordinate has nothing to do with it, make our maths a bit easier. If we're shooting in that direction, that means that the y-coordinate is going to be 0. This is going to be whatever the thrust is. At the moment, the thrust is 10 for each cycle. So if we're managing to get in 240 frames per second, it's going to do 10 times 240. So it's going to be doing 2,400 pixels a second. If the frame rate is 60, then it's going to be doing 10 every frame. So after 60 frames in a second, that's going to travel 600 pixels, which is a radical difference. So instead, what we want to do is say, you know what, I wanted to go that far in 1 second. How far have we gone in this frame? And if the frame says, okay, we've gone this much of a second, then we only want to go that much. If it says, actually, it's been quite a computationally expensive frame, so this frame has actually taken half a second, yeah, we'll get quite laggy, then you want to be moving a lot further. So to do that, you say, okay, that's 1 second, however many pixels you want, multiplied by this proportion, and it will make that arrow the right size. So let's have a look at this, and it is as simple as just multiplying everything by the delta. At the moment we've still got it at 10, so we'll want to update that to something a bit more reasonable. Let's say 1,000. So it will keep it at a good speed. Let's try that. Okay, that's going at the right speed. However, it's killing it way too quickly, because if we look at the code, we've got the lifespan, which is times minusing the thrust, where it should be moderating that thrust, so it's how much is it actually moving, not how much is the thrust. So try that again. There we go. So that's looking okay. So we essentially need to do the same thing for each of the others. So we have the ship, and we're going to be multiplying that by the delta on each side. Then we say, okay, what do we actually want? What thrust are we adding when we press the up? And this is going to be really weird. So that's really slow, because we're really not adding much to the thrust, because this is going to be how much per second. We've changed the units essentially. We've made these numbers actually meaningful, rather than just numbers which we're plucking out. So let's go for 20, and so we're adding 20 pixels per second to the thrust. Let's have a go at that. There we go, that's handling quite nicely. Handling so nicely that I'm able to crash straight into an asteroid. But I quite like that. Okay, and the asteroid isn't quite moving at the right speed, so let's do the asteroid as well. Whoops, shouldn't have been in the brackets. And then the thrust, how much do we want the asteroid to move in a second? And 100 pixels is probably about right. Let's have a look at that. Okay, there we go. So those asteroids seem to be moving at a reasonable speed for me. Now, if we change the frame rate, at the moment, each frame is taking 16 milliseconds. If we change the frame rate, so it's 240, now we shouldn't actually notice a difference in speed. Okay, we do on the spinning, but not on the moving, so we got an issue in there somewhere. Let's go to the ship and see what it's doing wrong. So I'm guessing that where we're changing the direction, we're not changing the rotation at the same rate. So if we multiply that, have a look at that, and this is going to be consistent. However, it handles awfully. So we need to get it so it's rotating a bit better. Try rotating 20 pixels each time. That's a bit better. And there we go. So that is now going to be the same handling for whichever speed we have. So let's change that back to... Actually, let's change it to 30. Really slow it down. So it's a bit jittery because it's only 30 frames a second. However, the handling and all is the same. So that's how to use delta in your programs to make things a bit smoother and make it so it's reliable and consistent on how things are going to behave. Hope it's of use.